Okay, welcome back to the lectures on transform calculus, and in the last lecture we were discussing about the integral representation of a function, and then we arrived at cosine and sine Fourier transform. So, we will continue from that point. So, let me just recall again what we had in the last lecture. So, we started with this Fourier integral representation, and so a function f can be represented, and here the function is not periodic, by this integral 1 over pi 0 to infinity minus infinity to plus infinity f u cos alpha u minus x du d alpha. So, this was in the last lecture, and we can also write this in this form, that f x can be represented by the same function, but we have introduced this a alpha and this b alpha, and this a alpha 1 over pi minus infinity to plus infinity f u cos alpha u du, and b alpha is 1 over pi minus infinity to plus infinity f u sin alpha u d alpha. And then we have seen that for an even function, so when the function is even, so we have this even times this odd. So, this integral over this symmetric interval will go to 0. So, b alpha will be 0, and we have simple this sine Fourier sine integral representation. So, that is, and in fact, this a alpha also we can just write 2 times of this 0 to infinity. So, what we have at the end, that this f x is 2 over pi and 0 to infinity, and then from here again 0 to infinity, and f u cos alpha u du, and this cos alpha x d alpha. So, this was for the even function, and I put here equality. So, I assume that this integral is absolutely integrable and all other conditions are satisfied, so that we have exactly equality here, or in a more general case we can replace this by the average value. So, and then we have defined the Fourier cosine and Fourier sine transform. So, exactly at this point, so what we take the factor square root 2 over pi and 0 to infinity f u cos alpha u du, and we since this is a function of now alpha, we are integrating over u. So, we call it this f and c for the cosine, and het this alpha, or we also write in this operator form that this f c, that is the Fourier cosine transform of f, will be given by this function, and then this f x would be with this notation 2 over pi. Again this is square root 2 over pi left here, and then we have 0 to infinity and this f hat. So, we are here, so f hat c alpha, and then this cos alpha x dx, and this is our f x, and this we simply call that the inverse Fourier cosine transform. So, f c inverse of this f c hat alpha. So, this is the inverse Fourier cosine transform. And similarly for the odd function, so if we take f to be an odd function, then we have the Fourier sine transform of f x. So, this is the notation for the Fourier sine transform, and we denote this integral by f s hat alpha, and this integral is as we can see again, because for this odd function this is going to be 0, this is odd, and this is even. So, we have here the odd integrand. So, this integral will be 0, and we have only this b alpha. So, then we can define this as we have done for the cosine, and this is the Fourier sine inverse, which is square root 2 over pi, and this f s alpha sin alpha x d alpha. So, this is inverse Fourier sine transform, and this is Fourier sine transform. So, we ended up the last lecture at this point, and now we will continue with just one example and then go for the Fourier transform. So, let us go for one example here. So, find the Fourier sine transform of e minus x x positive, and then show that the integral 0 to infinity x sine mx over 1 plus x square dx is pi e minus m over 2 m positive. So, now we go with the definition of this Fourier sine transform. So, e minus x square root 2 over pi 0 to infinity, we have e minus x, that is the function, and sine transform, then sine alpha x dx. So, we can evaluate this integral. So, let us assume this is I. So, we have I 0 to infinity e minus x sine alpha x dx. We integrate by parts. So, this the integral here we have minus e minus x and sine alpha x 0 infinity, and then minus 0 infinity again with this minus e minus x, and sine will give cos alpha x into alpha dx. So, here when x approaches to infinity, this will be 0, and when x approaches to 0, this sine alpha x will be 0. So, here we do not have any term. Now, we have this minus minus plus. So, we have alpha, and then again we integrate. So, minus e minus x and this cos alpha x, again limit 0 to infinity, minus 0 to infinity e minus x, and then we have this minus sine alpha x again 1 alpha dx. Okay, so here when x approaches to infinity, this will be 0, and of course this is bounded. So, this whole will go to 0, and when x to 1, then we have here 1. So, we will get this 1. So, 1 minus minus will be plus. So, here we have again this minus and alpha, and this sine e power minus x and sine alpha x, e power minus x sine alpha x, that is I. So, we have this, or now this I we can take to the left hand side. So, what we have I, this implies I plus alpha square I, and then we have is equal to alpha. So, this implies that I is alpha over 1 plus alpha square. So, now we have this I, and we got this f sine transform of this e power minus x. So, square root 2 over pi, and then we will replace with this I. So, we have basically f s e minus x, Fourier sine transform of exponential minus x 2 over pi alpha over 1 plus alpha square. And now, we take inverse Fourier sine transform inverse Fourier sine transform. So, we will get e minus x, and that was our f x. So, the first part is over. The second, we are going to get this integral 0 to infinity x sine m x over 1 plus x square dx. So, for that we take the inverse sine transform, and this is square root 2 over pi and 0 to infinity, and we have f s e minus x sine alpha x d alpha for x positive. So, this is what we got already, 2 over pi 0 to infinity f s e minus x is square root 2 over pi and alpha over 1 plus alpha square, and we have this sine alpha x d alpha for x positive, and now we change x to m to get this. So, we change this x to m just to have a different name here. So, we will get this pi by 2 it can take to the left hand side. So, pi by 2 e power minus m, x is changed to m. So, what we have now here 0 to infinity and alpha over 1 plus alpha square and sine alpha m d alpha. So, this we got the value of this integral. Okay, so we now proceed to define Fourier transform. So, for that we will again start with this Fourier integral, that is the fundamental concept we have. So, we got this Fourier integral, and that was this f x is 1 over pi 0 to infinity and minus infinity to plus infinity f u cos alpha u minus x du. Okay, now we note that this integral minus infinity to plus infinity f u cos alpha u minus x du is a even function of alpha, because if we change this alpha by minus alpha, this integral will remain the same. So, what we have then, what we can write in this case. So, let me write down. So, note that this integral minus infinity to plus infinity f u cos alpha u minus x du is n. So, what we have du and then d alpha. Okay. So, we get this f x here is an even function of alpha, then this f x, what we can write, it's we will take this 1 over 2 here pi, and this instead of 0 to infinity we will put minus infinity to plus infinity, because this integrand for this integral. So, our this integrand minus infinity to plus infinity f u cos alpha u minus x du is an even function. So, here we have straight away the 2 times 0 to infinity, and this 2 will cancel and we will get that integral. So, that is the trick. And also what we can have, if we consider this integral 1 over 2 pi and minus infinity to plus infinity, and again minus infinity to plus infinity f u, similar but with the sine alpha u minus x du d alpha. And now in this case this is an odd function of alpha, or function of alpha, and in that case, since this is odd, so minus infinity to plus infinity will give us 0. So, this is just simply 0. So, we have second equation. Now, what we do, we equation first and I multiply to the equation 2 to have the complex form of this Fourier integral simply. So, what we will get in this case, now the f x is 1 over 2 pi and minus infinity to plus infinity, this is common, again minus infinity to plus infinity, this second integral is common, and we have f u. So, cos alpha u minus x and plus I sin alpha u minus x. So, that again in exponential term we can write. So, f u and e I alpha and u minus x du d alpha, and this is called complex form of Fourier integral. Fourier integral. So, in this complex form, or just we rewrite now this to define Fourier transform and Fourier inverse transform, minus infinity to plus infinity and minus infinity to plus infinity, again f u e I alpha u du, that is one integral, and then we left here e minus I alpha x and d alpha. So, if we let now this together with the factor 1 over square root 2 pi. So, let f hat alpha 1 over square root 2 pi minus infinity to plus infinity and f u e I alpha u du, then this f x will be again the same factor 2 pi and square root 2 pi minus infinity to plus infinity, and this f hat alpha e minus I alpha x d alpha, and this is called, the first one here is called Fourier transform. Fourier transform of f x, and this is here is called inverse Fourier transform. Inverse Fourier transform of f hat alpha of this. And there are different versions available for this Fourier transform and inverse Fourier transform, because what we could have done here, instead of this adding plus I and multiplied to equation 2, we could have subtracted here with minus, then we will get here minus, and here we will get minus, and then we will get here plus. So, that could be another version of this Fourier and inverse Fourier transform. The another point that we have taken this 1 over square root 2 pi, this factor 1 over square root 2 pi, and then the other factor 1 over square root pi to have same prefactor here in the both cases. But what we can also do, that we can take either with this Fourier transform the complete factor 1 over 2 pi, or with the inverse Fourier transform. So, that is possible. So, what we also denote here as in case of the sine and cosine transform, that this we will call this Fourier of this f with big F, and in this case we will say Fourier inverse of this f hat alpha. So, that is the notation we will be using for the Fourier and inverse Fourier transform. So, now we have introduced this Fourier transform and inverse Fourier transform, and we will go for some important properties of the Fourier transform now. So, properties, first as usual we have linear property, and in this case if the Fourier transform of f plus b j is a Fourier transform of the function f plus b Fourier transform. So, Fourier transform of the function g x, and f x we can put here f x g x. So, this is no need to prove, it is just coming due to that linear property of the integral. The second one we have the shift property, and in this case the Fourier transform of f x minus a is e I alpha a and Fourier transform of f x. So, if we go to the proof, we take the Fourier transform of f x minus a as 1 over square root 2 pi and minus infinity to plus infinity. We take this f x minus a. So, f x minus a e I alpha x dx. So, 1 over square root 2 pi minus infinity to plus infinity. If we just substitute here substitute x minus a new variable t, the limits will remain minus infinity to plus infinity, but here we will have f t now, and e I alpha for x we have a plus t dt, and this e I alpha a we can take out of the integral, that is the constant with t. So, 2 pi and then minus infinity to plus infinity we have f t e I alpha t and dt, and this is again with this factor. This is the Fourier transform of f. So, we have e I alpha a and Fourier transform of f x. Now, the third property we have the translation property. Translation property, and in this case the Fourier transform of IAX f x will be translated to its Fourier transform. So, for alpha will be alpha plus a. Proof is very simple. So, Fourier transform of IAX f x, as per the definition, we have 1 over square root 2 pi and minus infinity to plus infinity e I a x e I alpha x f x dx. This is our function, and this is for the transform, I alpha x for the transform. So, now minus infinity to plus infinity, and we combine these two. So, I, and then we have a plus alpha, and x we have f x dx, and if you just see the definition of the Fourier transform, this is exactly f hat, and if we replace this alpha by a plus alpha here. So, now the next property we have the Fourier, and the most important which will be used for the application. So, Fourier transform of the derivatives So, in this case, if we have to have some assumptions here, that f x is continuously differentiable, so the derivative is also continuous, and f x approaches to 0 as mod x approaches to infinity, then so this ensures all the existence of this Fourier and Fourier derivative of this Fourier. So, then we have the Fourier transform of f prime x will be minus I alpha and the Fourier transform of f x. So, we go for the proof now of this property. So, Fourier transform of f x will be 1 over square root 2 pi and minus infinity to plus infinity. We have e I alpha x and this derivative of f with respect to x. So, we integrate by parts. So, square root 2 pi, and we have this integral of this f x and e I alpha x minus infinity to plus infinity minus again, and we have f x e I alpha x and I alpha, the derivative of this, and dx. So, as this x approaches to plus infinity or minus infinity, as per our assumption, this f x goes to 0. So, this term will vanish, and then we have here minus I alpha and this 1 over square root 2 pi with this minus infinity plus infinity f x e I alpha x dx will be the Fourier transform of f. So, if we have the generalized version of this, so if f x is continuously n times differentiable and the derivative of this x approaches to 0 as x approaches to plus infinity or minus infinity for k 1, 2 and n minus 1, and also for 0. So, the f(x) itself should go to 0 as x approaches to infinity. In that case, the Fourier transform of fn x will be minus I alpha, and we get here n, we get n and fx. So, this is the general result. Normally, we will be using for the second derivative while solving PDE. So, Fourier transform of the double derivative will be this minus I alpha square. So, minus alpha square and Fourier transform of fx. Then we have now the convolution property. So, this theorem says that Fourier transform of the convolution of f and g will be square root 2 pi and f of f and the Fourier transform of g. So, here this convolution is defined as, so f star g is minus infinity to plus infinity, that is the our range we are working, and then this convolution f y and g x minus y dy. So, this is the convolution of f star g x. So, now we go for the proof of this. So, the Fourier transform of this f star g of this convolution, by the definition we have 1 over square root 2 pi minus infinity to plus infinity f star g and e I alpha x dx. So, this is 1 over square root 2 pi, and we have minus infinity to plus infinity. Again this convolution we have minus infinity to plus infinity f y and g x minus y dy e I alpha x and dx. Now, we change the order of integration to simplify this. Change the order of integration, then we will get 1 over square root 2 pi minus infinity to plus infinity. So, we assume that this is possible here to change this order of integration without going into the detail, and we have this f y g x minus y e I alpha x and dx dy, and we now substitute this x minus y to a new variable t, such that we have dx to dt. So, now we get 1 over square root 2 pi and minus infinity to plus infinity, minus infinity to plus infinity f y as it is, and g, this x minus y is now t, and we have e I alpha, and there was a x, so that is y plus t, and we have dx is dt now and dy. So, we have substituted this, and now what we see that we multiply this 1 over square root 2 pi to get 1 over square root 2 pi once again. So, once this is sitting here anyway, that is coming minus infinity to plus infinity, and we have multiplied. So, we will also divide here. So, first we collect for the y, which is independent of the inner integral. So, f y and e I alpha y from here, and then we put that 1 over square root 2 pi here. We have the inner integral with respect to t. So, g t and e I alpha t from here, and we have dt, and then we have dy. So, this one, that is the Fourier transform of g. So, we have square root 2 pi. So, that is the Fourier transform of g, and then the remaining one f y I alpha y dy, that is the Fourier transform with this. That is Fourier transform of f. So what we have here, f at alpha and g hat alpha, or we can write in this operator form that the Fourier transform of f and multiplied by the Fourier transform of this g, and this was the Fourier transform of f star g. So this is the convolution theorem we have. And now we go for one more important result, that's called the Parseval identity. So Parseval's identity for Fourier transform, Parseval identity. So there are basically two identities, one is generalized and one is a particular case of that. So we have f hat alpha and g hat alpha with complex conjugate. If we integrate this with respect to alpha, this is minus infinity to plus infinity f alpha and g x complex conjugate. And the second identity, that's just a particular case of this, and this f hat alpha square d alpha minus infinity to plus infinity, we have fx and dx. So go for the proof for the first one. So we start with this, so minus infinity to plus infinity, and fx g is complex conjugate dx, and minus infinity to plus infinity, and we have this fx, and then this by inverse transform, we have 1 over square root 2 pi and minus infinity to plus infinity. So the inverse transform of this g, we are writing the transform was g hat alpha and e minus I alpha x d alpha and dx, and this complex conjugate of this term. So we have minus infinity to plus infinity fx multiplied by, so 1 over this square root 2 pi, we have minus infinity to plus infinity, and this will be g hat alpha complex conjugate and complex conjugate of this, which is e I alpha x d alpha dx. And now we can change the order of integration. In this case, then we will get, so minus infinity to plus infinity, minus infinity to plus infinity, 1 over this square root 2 pi, we have fx, we have g hat alpha, and we have this e I alpha x, what else we have, then dx, and we have d alpha. So this 1 over square root pi fx e I alpha x with this dx will give us again the Fourier transform of f. So this is the Fourier transform of f, and we have already this Fourier transform of g with this conjugate and d alpha. So the first result is proved, and for the second one, that's just a particular case. So if we take this f and g same function, then we will get the second result. So taking fx is equal to gx, what we will obtain minus infinity to plus infinity fx and fx bar dx, and minus infinity to plus infinity f hat alpha and f hat alpha complex conjugate, and this is, we can also write this fx whole square and minus infinity to plus infinity f hat alpha square d alpha. So now we have reviewed some properties of this Fourier transform. So we go for some interesting examples before we go for the real application. So the example, find Fourier transform of exponential minus ax square. So for this solution we have Fourier of exponential minus ax square, thus by the definition 1 over square root 2 pi minus infinity to plus infinity and e I alpha x and the function e minus ax square dx 1 over 2 pi and we have minus infinity to plus infinity e power, we combine these two minus a and we have then x square and minus, so here I alpha over a and this x, yes, and then dx. So now we have 1 over square root 2 pi minus infinity to plus infinity and e minus, we try to put here in a whole the complete square form. So we have x minus I alpha over 2a and whole square, then what we will get x square, and this plus square of this term is extra here, so we will compensate that, but we have this 2 times the multiplication of this, and this is x I alpha over a, so that term is here. So what additional term we have here? The square of this, so that is I square alpha square 2a square. So we have I square is minus 1, so alpha square over 2a and minus was here, so we have plus alpha square over 4a because the 2a whole square. So with this 1a square is cancelled, so we have here the extra term e power plus alpha square over 4a. So then we have to subtract that alpha square over 4a and dx. Now we can substitute this so that we have here whole square, so square root a and x minus I alpha over 2a, we put it as y, so that we have dx is dy over square root a. So if we do that, what is our Fourier transform of e minus ax square is 1 over square root 2 pi and we have minus infinity to plus infinity, so this is e power minus y square and this e minus alpha square over 4a, it is and this dy over square root a. So this is 1 over, so here minus infinity to plus infinity e minus y square dy, that's a Gaussian integral and the value is square root pi, so that will be cancelled with this. So this is anyway constant, we have taken out of this integral. Now we can take this, so 1 over square root 2 and the square root a is here and e power minus alpha square over 4a. So this square root pi gets cancelled with this integral minus infinity to plus infinity e minus y square dy, value of that integral is square root pi. So here we had 1 square root pi, so this is cancelled. So this is the Fourier transform of e minus a x square. And just to note that if we take a is equal to half here, so taking a is equal to half, what will be the result? E power minus x square by 2 will be, a is half, so this term is gone now, so e power minus alpha square over 2, e power minus alpha square by 2. So what this shows that Fourier transform of e or in general Fourier transform of this fx. So Fourier transform of e power minus x square by 2 is just e power minus alpha square by 2. So we replace just x by alpha, so this is f alpha. It's interesting, and such functions or such function which hold where this property holds is said to be self-reciprocal under Fourier transform, under Fourier transformation. Okay, so this function e power minus x square is self reciprocal under this Fourier transformation. Take another example now. Find the Fourier transform of ft e minus a, and absolute value of this t is minus infinity to plus infinity. So the solution e minus at, as per the definition, we have 1 over square root 2 pi, and we break that integral minus infinity to plus infinity into two parts. So minus infinity to 0, and we have e power this modulus or absolute value of t in this range we can replace by minus t. So we have a t e I alpha t and dt plus then 0 to infinity, and this will be e power minus, because absolute value of t will be just t e power minus a t e I alpha t and dt. So what we have 1 over square root 2 pi, and again I can just write this. So it's e power a plus I alpha t dt plus 0 to infinity e power minus a plus I alpha t dt. Now we can integrate this. So 1 over square root 2 pi, so e power a plus I alpha t over a plus I alpha minus infinity to 0 plus e minus a plus I alpha over minus a plus I alpha and 0 to infinity. So 1 over square root 2 pi, and this when we put 0 we get 1 over a plus I alpha minus infinity, this term will go to 0, and similarly when we put this t approaches to infinity, this term will go to 0, because we have e power minus a t and multiplied by e power I alpha t. So that is bounded, and e power minus a t, for the same reason what we have here, this will approach to 0, and we have minus 1 over a plus I alpha, minus a plus I alpha. Okay, so 1 over square root 2 pi, and then we have this the common factor here, a plus I alpha, and we take a minus I alpha, so that here is plus, so that will be a square plus alpha square, and here a minus I alpha, then this will be plus a and plus I alpha, so this will be cancelled, and we have 2a over square root 2 pi and a square plus alpha square. So that's the result. Okay, so the next example, we have Fourier transform of Dirac delta function. We have introduced this function already while discussing the Laplace transform. So just to recall, it was the delta t minus a, and we considered this as a limit of this delta epsilon function. So just remember, this delta epsilon t minus a was 0 and 1 over epsilon, and again 0 when t is less than a, and when t is between a and a plus epsilon, and when t greater than again a plus epsilon, it's 0. So with this definition we have seen that this minus infinity to plus infinity fx delta x minus a dx as fa, and with this definition we can easily get this Fourier transform of this delta Dirac delta function, which will be 1 over square root 2 pi minus infinity to plus infinity with this definition t minus a e I alpha t and dt. So this will give us the function value, so that's e power I alpha a, so 1 over square root 2 pi and e I alpha a. In particular we have when a is 0, so the Fourier transform of delta t is simply 1 over square root 2 pi, because a is 0, so this is 1. Or this also implies that the Fourier inverse, if we take of this 1, so take the Fourier inverse both side, so this will be square root 2 pi go to that side and the delta t. So this also a result we will use. We have two more special examples where we will evaluate some special integrals, and the first example in this category, find the Fourier transform of fx defined by fx 1 and 0 when x is less than a and when x is greater than a, and hence evaluate the integral minus infinity to plus infinity sine alpha a cos alpha x over alpha d alpha, and also 0 to infinity sine alpha over alpha d alpha. So for the solution, so we have found Fourier of this fx is defined between minus a and a, so 1 over square root 2 pi, outside that it's a 0, so 1 over square root 2 pi minus infinity to plus infinity e I alpha x, and we have fx dx, so 1 over square root 2 pi, and this is from minus a to a, outside this interval this fx is 0, so in this range it's 1, so we have I alpha x and dx, so it's simple now, 2 pi, and this is e I alpha x over I alpha, and our limit minus a to a. So what we have then, 1 over square root 2 pi 1 over I alpha and e I alpha a minus e minus I alpha a, and with this I factor, and we can have already this I we can multiply and divide by 2, so to get this, so 2 over square root 2 pi, and this will be sine alpha a over alpha, and this is our Fourier transform of this function for the given function. Okay, now we go for this evaluation of this integral. We have two integrals there, and always we have such integrals, and we can take this Fourier inverse transform, and this factor will sit then inside the integral, and that we know already that this is f(x) is equal to that integral, so we can get the value. So we know now for the from the inverse Fourier transform that f(x) is 1 over square root 2 pi and minus infinity to plus infinity f hat alpha e minus I alpha x d alpha. At this point of this continuity, we have this equality holds, and otherwise we have the average value in any case. So what we have now, 1 over square root 2 pi and this integral minus infinity to plus infinity, f this alpha was 2 over square root 2 pi and sine alpha a over alpha and e minus I alpha x d alpha as f(x). So what we have now, this square root 2 pi will be, and this 2 we can cancel, so we have 1 over pi that will go to the right side of this integral. So we have minus infinity to plus infinity, and this sine alpha a, and this is cos alpha x minus I sine alpha x over this alpha and d alpha. This is equal to pi and this f(x), and we know already that this f(x) is 1 when x is mod x is less than a. So this will give us pi simply when mod x is less than a, and this will be 0 when this absolute value of x is greater than a. Now we equate the real part, so we get minus infinity to plus infinity and sine alpha a cos alpha x over alpha d alpha, and the value of this integral is pi and 0 if x less than a and if x greater than a. So that was the one part of the question. For the second one, we need to have this sine alpha over alpha. So what we do in this case, that x if we put 0, so take this x to 0. If we take this x 0 and let's take this a1, so a1 and x 0, so the value would be pi of that integral. So what will be the integral now? Minus infinity to plus infinity, and this a is 1, so we have sine alpha over alpha and cos 0 will be 1, so this d alpha, and the value now, because this mod x is less than less than a, so this value will be just pi. So this integral we have evaluated. Similarly, the very last example we go through quickly. So if we have the f(x) 1 minus x square and 0, mod x is less than 1 and mod x is greater than 1, it's 0, and in this case we can evaluate such an integral. So evaluate 0 to infinity minus x cos x plus sin x over x cube dx. So we take the Fourier transform of this f(x), 1 over square root 2 pi minus infinity to plus infinity e I alpha x f(x) dx. So we have 1 over square root 2 pi and minus 1 to 1, because outside this the f(x) is 0, e I alpha x, and then we have 1 minus x square dx. So 1 over square root 2 pi, and this we can integrate and we will get at the end. So I am writing just directly the value. So we will get 4 over alpha cube and minus alpha cos alpha plus sine alpha, and this is f hat alpha. And we know again from the Fourier inverse transform, that f(x) is 1 over square root 2 pi minus infinity to plus infinity, and this function e minus I alpha x d alpha. So we substitute here and again take the real part. So equating real part, we will get minus infinity to plus infinity minus alpha cos alpha plus sine alpha over alpha cube and cos alpha x d alpha, and the value would be pi by 2 f(x), and this is pi by 2, and value of the f(x) we have 1 minus x square if mod x is less than 1, and this is 0 if mod x is greater than 1. So if we put here the x is equal to 0, so in that case, so this cos 0 will be 1, and we have minus infinity to plus infinity minus alpha cos alpha plus sine alpha over this alpha cube and d alpha, and when x is 0, so it's less than 1, so the value is pi by 2. And this is, if we see, this is the even integral. So if we put alpha to minus alpha, we will get the same value, because here we'll get minus and then minus here. So this is the odd even function. So we have 2 times the 0 to infinity and minus alpha cos alpha plus sine alpha over alpha cube and d alpha. The value is pi by 4, because 2 will go to this side and we have pi by 4. So today we have discussed this Fourier transform with the help of various examples, and in the next lecture we will go for the application to partial differential equations. So and we will consider 3 different kind of partial differential equations as in the case of Laplace transform. So then for today's that's enough, and thank you.